Good morning. I am going to go over the worksheets. This is the worksheets number 3, the end of the chapter, where they throw in the mole concept. Now this relates to what we were doing because we were talking about atoms and the need to count atoms in large groups of atoms. So we introduced Avogadro's number, which is a value that we can write as a factor like any other conversion factor. The thing that's odd about it is it's got a number and a unit on the top, and it's just got the number on the bottom. So I had written this as a conversion factor where I could say 1 mole on top and 6.022 times 10 to the 23rd on the bottom. And that's true for any object. That's just like a dozen or a pair. You could have a pair of gloves, you could have a pair of socks. So the label will be the same on the top and on the bottom. We could think about a mole of roses. That would be this many roses. And that's a huge number. Have there been that many roses? I frankly don't know. It's very hard to conceive of how big that number is. Okay. So I did cover the parts A and B here, so I'm going to use that factor. I'll keep that on screen. So I had started this question here, part C, how many moles of carbon atoms? Now carbon comes as atoms because it's an element. So you could just think of that as how many moles of carbon. For example, if I said how many reams of paper are in the supply closet, I wouldn't say how many reams of pages of paper are there? I would just say reams of paper. We know they're going to be pages of paper. So in the same way, moles of carbon, yes, those will be carbon atoms. And I could even have moles of a molecule. I could say how many moles of water, and that would imply molecules because water comes as a molecule. Okay, so when I write down this question, I'm going to write how many moles, so my number and my unit, and my label, how many moles of carbon are present. That is my equal sign. And then here's the value I'm starting with. 1.25 times 10 to the 24, so that's large. 1.25 carbon atoms. And I want to use the units to change that into moles. So I will need to get rid of carbon atoms down here, and I want to go to moles up here. So then we need to fill in the numbers from our factor. Oh well, we're not talking about roses anymore. So the 1 goes with the moles. So let's put a 1 there, and we'll put the value down there. And then we'll calculate. So give me a moment. I advise that you use your exponential button, your EXP or EE, and I get 2.0757 moles of carbon, and that is good to 3 significant figures. So if I was going to round that, I would say it's about 2.08 moles of carbon. Now, moles has the abbreviation MOL. One thing that we can notice about moles, when we're talking about moles, that's going to bring that huge number, right, this huge exponential number, is going to bring it into a value that is normal for us, 1 to 20, right, the number of digits we have. So when we talk about moles, we have a number that we can relate to, a nice normal number like 2.08. Whereas when we talk about individual atoms, we're talking about a huge collection of particles, so many that we couldn't even count those individually in our lifetime. Okay, now the cool thing about counting in moles, and the reason we use it for our counting number, is that it turns out that that mass translates directly into grams. So based on our atomic mass unit that we set up originally a couple pages ago, we can write the mass reported on the periodic table either as atomic mass units, so the mass of one atom, or we can use the units grams per mole. So what we're saying is, for example, carbon, we'll look at carbon, that if we measure 12.01 grams of carbon, then we know that we have 1.000 moles of carbon. So that's very handy. We can look at it on the individual atom level, or we can take a collection, so this is a large number of atoms, a big collection, and just weigh it on the balance. That's something that we can access in lab. 12 grams of carbon, that's like the small pile that we named the mole after. What that means is we can use the molar mass from the periodic table. Periodic table, that is the mass of 1 mole, straight off of the periodic table. I buried mine. So aluminum, we find aluminum, it's number 13, and the number underneath it is 26.98. We can take that number and give it the units grams per mole. 26.98 grams of aluminum in 1 mole of aluminum. That's easy to measure. We can measure that. Let's look at silicon. It's right next to aluminum. That is 28.09 grams of silicon in 1 mole of silicon. So don't be fooled by that slanty line. I'm going to go ahead and write one like that. Let's look at argon, number 18. That is 39.95 grams per mole. That implies grams of argon on top, 1 mole of argon on the bottom. And tin, SN. Tin is number 50, and it shows up as 118.7 grams of tin in 1 mole of tin. So we'll see it referred to this way like we did for argon, but when we use it in calculations, we'll want to use that clear numerator and clear denominator. So we'll use this as a conversion factor to solve our problem. So here's an example. How many moles of helium are in 5 grams of helium? So let's apply our dimensional analysis to that. How many moles of helium are in 5.00 grams of helium? So using dimensional analysis, I'll erase that, it's a little close. We need to cancel out grams of helium and go to moles. 1 mole of helium must weigh how many? Well, we'll go look for that. We find it on the periodic table, so we'll line it up down here. 4.003 grams of helium. Now I'm going to use an extra digit on that mass. So I'm taking the mass to 4 significant figures when my data has 3 significant figures. And that ensures that I'm not including rounding error. So I'll just divide that. 5 divided by 4.003, and I get 1.249, good to 3 sig figs, moles of helium. How many atoms would that be? How many atoms? We're going to need to use Avogadro's number. So I'll write that as a factor up here. Na, Avogadro's number. That says 1 mole has 6.022 times 10 to the 23rd. Now in this case we're looking at helium, so we could just say a mole of helium has that many helium in it. So how many helium atoms equals 5 grams of helium? Well, we just did this above, and we see that there are moles here using Avogadro's number. So we want to get to moles. When in doubt in chemistry, go to moles. Calculate your moles. So I'm going to use that same factor. 1 mole of helium has 4.003 grams. Grams are out of there. Now I need to cancel out moles of helium in the bottom and get to helium atoms. So be careful when you do this. Make sure you put the number in the right place. 1 mole of helium has 6.022 times 10 to the 23rd helium atoms. Let's show those units canceling, and then we get helium atoms equals helium atoms. Now, if I wanted to substitute this section of the calculation with the value above, I would use the unrounded value. We need to keep an extra digit there. Then multiply that by 6.022 E23, and I get 7.5218 times 10 to the 23rd helium atoms. Good to 3 significant figures, so that would round to 7.52 times 10 to the 23rd. Let's do another example. An aluminum can weighs 16.55 grams. How many moles of aluminum are in that can? So let's see, we're looking for moles of aluminum. How many moles of aluminum equals 16.55 grams of aluminum? So I can, here's my number, here's my unit, and then here what we're talking about, this is our label. Sorry, that's not super clear. All right, we need to cancel out grams of aluminum and go to moles of aluminum. And we know that 1 mole has, and we just did this up at the top, that is 26.98 grams. All right, so our units tell us we did it. That's it. I'm going to keep an extra digit showing. Oh, not silver, aluminum. We had 4 digits to start with, so this is 0.6134 moles of aluminum. Well, how many atoms are in that can? So how many aluminum atoms? I just found moles, so I can use that value here. I could also rewrite it. Now in this case, I'm going to keep that extra digit to make sure I don't have any rounding error introduced. Okay, we need to cancel out moles of aluminum, and we're looking for atoms. So we'll use that factor again and figure out where the numbers go. 1 mole of aluminum is 6.022 times 10 to the 23rd atoms. So I will multiply those. And I get 3.6939 times 10 to the 23rd aluminum atoms, which will round to 6.394 times 10 to the 23rd aluminum atoms. Now a couple more little tips. You can always do a ballpark check and think about how big is that number? Is that a big number or a small number? right here, 0.6 moles, yeah, it's kind of small, but that's a normal number. We're used to. If I said, can you give me 0.61 of an apple? You could cut it roughly in half and give me the big half. We know how big that is. But take a look at this one. 10 to the 23rd, now that's a big number. So when we're talking about moles, we want a normal number that we can relate to. When we're talking about atoms, how many particles, how many molecules in a glass of water, that kind of thing, how many pieces, particles of an element or a molecule, then it's going to be huge. It's going to be a large number. And that will help determine whether you made a mistake in multiplying or dividing with this factor here. So it's good to look at it and see if you have the right number. Another reason that that's so helpful is that students will sometimes write down this first part of the number and they forget the exponent. So if you just build in a little step, a little moment of looking at it and saying, is it big or small? Is it big enough? If you get 6.3 atoms, well, it's probably not something that you're holding in your hand that you can weigh. So there's a little ballpark check built into that. Oh, whoops, I erased too much. All right, we're gonna start talking about ions probably before the exam, but it's covered in one of the sections of this chapter, but we're just right now going to be aware of what electrons are, where they live, how their mass and charge relate to the other subatomic particles. We will not start adding and removing electrons to form ions until a little later. So I just like to create a break in the content because it's easier, I think, to get really clear on what an isotope is if you're not worrying about charged particles. We are going to talk about neutral atoms a while longer. Okay, I think that wraps up chapter 3. Oh yes, I did have one more thing I wanted to talk about. The gizmo for the moles calculation. That could be a really useful way to practice setting up these calculations without having to start from scratch. So maybe I'll do that in a separate video. Thank you. Have a good afternoon.